Chapter 9, Estimating the Value of a Parameter. Section 9.1, Estimating a Population Proportion. We will look at these three objectives in this section. First, let's look at the definition of a point estimate. A point estimate is the value of a statistic that estimates the value of a parameter. Remember that a statistic is coming from a sample and a parameter is coming from a population. So for example, the point estimate for the population proportion is p hat, which is given by the equation x divided by n, where x is the number of individuals in the sample with a specified characteristic, and n is the sample size. Objective 1. Obtain a point estimate for the population proportion. In this first example, we're looking at calculating a point estimate for the population proportion. In July of 2008, a university poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. So we want to obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So remember that our point estimate for a proportion is given as P with this little hat on top, or P hat. And the formula is x over n. So x is the number of people who are in favor of the death penalty, and that was 1,123. And we're dividing by n, which is the sample size, which is how many voters were asked total, and that was 1,783. So when we evaluate this, we get approximately 0.63 as our point estimate. Objective 2. Construct and interpret a confidence interval for the population proportion. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. So we can't always know exactly, but we can find out within a certain interval that our value for the population will fall within that. And we use a level of confidence. This represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted this way as 1 minus alpha times 100%. So it's typically given as a percentage. For example, a 95% level of confidence, or alpha equal to 0.05, implies that if 100 different confidence intervals are constructed, each based on a different sample from the same population, we will expect 95 of the intervals to contain the parameter and 5 not to include the parameter. So confidence interval estimates for the population proportion are of this form. We use the point estimate plus or minus the margin of error. And the margin of error of a confidence interval estimate of a parameter is a measure of how accurate the point estimate is. The margin of error depends on these three factors. First, the level of confidence. As the level of confidence increases, the margin of error also increases. It also depends on sample size. As the size of the random sample increases, the margin of error decreases. And lastly, it depends on the standard deviation of the population. The more spread there is in the population, the wider our interval will be for a given level of confidence. So let's look at the sampling distribution then of p hat, which is the point estimate for the proportion. For a simple random sample of size n, the sampling distribution of p hat is approximately normal with the mean, mu with a subscript of p hat, equal to p, and the standard deviation, sigma with a subscript of p hat, equal to the square root of p times 1 minus p divided by n, provided that n times p times 1 minus p is a value that's greater than or equal to 10. So note, we also require that each trial be independent when sampling from finite populations, and that the sample size n is less than or equal to 5% of the total population, or 0.05 times capital N. So let's look at constructing a confidence interval for a population proportion. Suppose that a simple random sample of size n is taken from a population. A confidence interval for p is given by the following quantities. The lower bound is our p hat or point estimate minus our z-value, z sub alpha over 2, times the square root of p hat times 1 minus p hat divided by n. And the upper bound is the same, except notice that we are adding. So also remember that it has to be true that n times p hat times 1 minus p hat is a value greater than or equal to 10, and our sample size n has to be less than or equal to 0.05 times capital N in order to construct this interval. So notice with the lower bound and the upper bound, we are subtracting in the lower bound and we're adding in the upper bound the same equation to our point estimate p hat. A confidence interval indicates that percent of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. So for example, if we're doing a 95% confidence interval, then we're saying that 95% of all of our simple random samples of size n, whose parameter is unknown, they'll result in an interval that contains the parameter. And the value that we were adding and subtracting for our upper bound and lower bound is what we call the margin of error. It's given by the letter E. In our confidence interval for a population proportion, it is the equation that we saw added and subtracted to our lower bound. Let's look at how we can determine the critical value, our z sub alpha over 2, that corresponds to the given level of confidence. So if I have a level of confidence of 92%, the first thing I want to do is I want to do 1 minus my 0.92, and then I want to divide that by 2. So when I subtract, I will get 0.08 divided by 2, and I'll get a value of 0.04. I then want to look in the table, and in our table 5, our standard normal distribution table, I'm looking in the middle area for 0.04. I see that this value here is the closest, 0.0401. And that z-value then is negative 1.75. But I want to use the positive value for it, so I get a positive value of 1.75, and that would be equal to my critical value z. So let's look at another example. Here we're continuing the example we looked at before, where we looked at whether or not voters favored or opposed the death penalty. We want to obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So remember that our p hat value we already calculated, and it was the number who were in favor divided by the total. And we calculated that and got a value of 0.63. That was our point estimate. And let's make sure that we can do this interval. So we need to check that n times p hat times 1 minus p hat, that is greater than or equal to 10, and that our sample size is less than 5% of the total population. So in the first case, we have 1783 times 0.63, and then times 1 minus 0.63, which will give us about 415.6, and that is definitely greater than or equal to 10. And our sample size, the 1783, is definitely less than 5% of the population size, since the population would be all registered voters, which is in the billions. So we know we're less than 5% of that. So we have an alpha value of 0.10 since we're doing a 90% confidence interval. So we want to find our z value, z sub alpha over 2. So we look at our table, and this is given on table 5, and we see that for 90% level of confidence that we have a critical value, or z sub alpha over 2, equal to 1.645. So our lower bound will be our point estimate minus the z value. This is our margin of error, times the square root of p hat times 1 minus p hat over n. So we have 0.63 minus 1.645 times the square root of 0.63 times 1 minus 0.63 over 1783, which will give us about 0.6112, or approximately 0.61 for our lower bound. Then the upper bound is going to be p hat plus that value, our margin of error, so we have our 0.63 plus 1.645 times 0.63 and 1 minus 0.63 over 1783, which is approximately 0.64488, or about 0.65 for our upper bound. So when we write our confidence interval, we'll put it in parentheses here and put 0.61 up to 0.65, and that would be our 90% confidence interval. And so what that means then is that we are 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is between 0.61 and 0.65. It is very important to note that the level of confidence refers to the confidence in the method, not in the specified interval. A 90% confidence interval means the method works, meaning it includes the unknown parameter for 90% of all samples. A 90% level of confidence does not tell us there's a 90% probability the parameter lies between the upper and lower bound. So let's look at the role of the level of confidence in the margin of error. Logic suggests that a higher level of confidence leads to a wider interval. The width of the interval is determined by the margin of error. In our last example, we'll look at the effect of the margin of error by increasing the level of confidence from 90% to 95%. So we're going to do the same example, except now we're going to look at a 95% confidence interval. And remember that our margin of error for before was 0.0188 for 90% confidence, and our interval had p hat being between 0.61 and 0.65. So p hat has not changed. P hat is still equal to 0.63. But now alpha is equal to 0.05. So when we take z sub alpha over 2, we have z 0.05 divided by 2, which would be z sub 0.025. So when we look at it on our table for 95% confidence, we get a value of 1.96. So our lower bound is equal to 0.63 minus our z-value, 1.96, times the square root of 0.63 times 1 minus 0.63 over 1783. And remember that this part is e, and if we just work out that part, we get 0.0224. When we subtract that from our point estimate of 0.63, we get a value of 0.6076. Now let's look at the upper bound. We have our point estimate plus 1.96 now, times 0.63 and 1 minus 0.63 over 1783. And remember that that was equal to 0.0224. Now we're adding it, so we get a value of 0.6524. So increasing the level of confidence increases the margin of error, therefore resulting in a wider confidence interval. Now let's look at that last example using the calculator to calculate our confidence interval. So the first step, we're going to press stat and arrow over till we highlight the tests category. Then we want to arrow down till you see the header A for 1 prop z int, and then hit enter. We want to enter the values we had for x and n. So x is going to be our smaller number, and that was our 1123. And then n is the larger number. So from our last example, that was 1783. Next, we want to enter the confidence level, and for our example, it was 95%, so we're going to put 0.95. Then lastly, we're going to arrow down and highlight calculate, and then we hit enter. And notice that we have our confidence level, and it's actually exactly what we got by hand to the third decimal place. 0.607 was our lower bound, and 0.652 was our upper bound. So this is a much faster way to calculate your confidence intervals about your proportion. Objective 3. Determine the sample size necessary for estimating a population proportion within a specified margin of error. The sample size needed for a specified margin of error, E, and a level of confidence 1 minus alpha is given here. We use the value of n for our sample size, and it's equal to p hat times 1 minus p hat, then multiplied by the quantity z sub alpha over 2 divided by our margin of error E, that is squared. We do have a problem. The formula uses p hat, which depends on n, and this is the quantity we're trying to determine. So there are two possible solutions to get around that. First, we use an estimate of p hat based on a pilot study or an earlier study. And the second thing we can do is let p hat be equal to 0.5 or 50%, which gives the largest possible value of n for a given level of confidence and a given margin of error. And we see a picture of that here. Notice up at the top of the picture, if we let p hat be equal to 0.5, then when we multiply 0.5 times 1 minus 0.5 in our formula, we'll get the value of 0.25. So when calculating the sample size required to obtain a confidence interval for P with a margin of error E, it's given by this formula here, P hat times 1 minus P hat times Z alpha over 2 divided by E, quantity squared. And this is important. It is rounded up to the next integer, where p hat is a prior estimate of p. So remember that we always round up, no matter how small the decimal is, we'll always round up to the next whole number. If a prior estimate of p is unavailable, the sample size required then is given by this formula. We use the value of 0.25, which we saw in our earlier picture, then times z alpha over 2 divided by e squared. So let's look at an example where we'll use both of these formulas to determine the sample size. A sociologist wanted to determine the percentage of residents of America that only speak English at home. What size sample should be obtained if she wishes her estimate to be within 3 percentage points with 90% confidence, assuming she uses the 2000 estimate obtained from the Census Supplementary Survey of 82.4%. So in this case, we do have a prior estimate for p hat. So our p hat value is equal to 0.824. Now let's find our z value, z sub alpha over 2. We look at our table and notice that we're trying to find our critical value for z for our 90% confidence level. So that's the value 1.645. Our margin of error, to find that, we want to look for the words within. And we see it here. And then the number after it is our margin of error. So E is going to then be equal to 3 percentage points, which is actually then equal to a value of 0.03. So we're now ready to use our formula for n, which was p hat times 1 minus p hat times our z value divided by e squared. So we start filling in. We have 0.824 times 1 minus 0.824. Then we have 1.645 divided by e squared. So I'll pull up the calculator and we'll show what this will look like when you enter it there. So this is how we would need to type it in and hit enter. And we see that we get a value of 436 with a decimal. So we get about 436.04. But remember, we're looking for the minimum sample size, so we need to make sure to round up. Even though the traditional rules of rounding would tell us to round down to 436, we need to make sure to round up. So we'll get an n value then of 437 as our minimum sample size. Now let's do the same example and assume that we do not have any prior estimates. So remember that our z value has not changed, so we still have 1.645, and our margin of error has not changed, it's still 0.03. The formula we use, however, has changed. Since we don't have a prior estimate, remember we're using a p hat value of 0.5, which when we calculated p hat times 1 minus p hat, that would have been 0.5 times 1 minus 0.5, which gives us a value of 0.25. So in our formula then, we're just using our 0.25 here outside of our parentheses, where we then have z divided by e squared. So I have 0.25 times 1.645 over 0.03 squared. And let's put that into our calculator. So this is how it would be entered, and we hit enter. And we see we get a value of 751 with a decimal. So we get about 751.67. Remember that we still have to round up, and in this case, our traditional rules would have had us rounding up anyway. But we get a value of 752 then for our sample size.